In this video, we're going to be taking a look at two masses that have an 80 Newton angled force applied on it. The first one has an 80 Newton force angled downward at 30 degrees, and the second one has the 80 Newton force angled upwards at 30 degrees. So we're going to compare and contrast these two situations to see which one has the greater acceleration and why. So let's go ahead and take a look at our first object over here. We have a bunch of different forces acting on it. So we're going to start off with drawing our force diagram on here first. We have Fg force of gravity pulling it straight down. We have the normal force pushing up perpendicular from the surface. And then we have this force over here, which we'll call an Fa, an applied force on the mass. And then because the object would be sliding to the right, we have a force of kinetic friction that would be opposing the slide. And in addition to that, I'm going to slide this right below it. If we want the force of friction, we're going to do the coefficient of kinetic friction times the normal force, which we're eventually going to use a little bit later. Now, a couple things are this. We want to set up the forces in the x and y direction. In the x and y direction, we have Fn and Fg, and then we have this angled force over here that we want to break up into two different components. We have a y component here and an x component here. So let's go ahead and pull that triangle aside. So that we can solve for those x and y components. Now, our 30-degree angle is over here because it's 30 degrees above the horizontal. So the end that's opposite of that is going to be our y component. So we can call that maybe Fay to be more descriptive, and we'll call this one Fax. So since we want to use the 80 newtons actually, 80 newtons as our hypotenuse, along with our opposite end, we're going to use the sine of 30 degrees because sine is the opposite over the adjacent side. So if we go ahead and set that up, then we have the sine of 30 degrees equals the opposite over, basically multiply both sides by 80, and then 80 times sine of 30 is going to be 40 newtons. Now the second thing we're going to do is we're going to do the same thing for the x component. We're going to go ahead and use the adjacent side to the 30-degree angle, and we're going to have Fax over 80 newtons equals the cosine of 30, and then do the same thing, multiply both sides by 80, and then that gives us our x component. Our x component comes out to be 69.28 newtons. All right, so that's the first thing you're going to want to do. I'm going to go ahead and include both of those values right up here so that I can clear some space to show the work for both of these two larger calculations. So we got the Fay is 40 newtons, and then we have an Fax of 69.28. All right, so let's go ahead and clear this previous work and then set up our formulas for everything in the x and y axis. So now that we have our two formulas set up, we have everything in the upwards direction as positive, which is only Fn, and anything that's directly downwards, which is our Fay and our Fg downwards. So we're subtracting those two, making those negative values equals m times a, and there is no movement or acceleration in the vertical direction, so we can say that's 0 newtons. In the horizontal direction, we have our FAX pushing it to the right, and then we have our FFK, our force of kinetic friction, opposing it going to the left, and that equals M times A. We know that M is 10 kilograms from the original question. That's where we're going to be able to solve for our A. So let's go ahead and plug in all of the values we know and see where that takes us for our next step. Now that we plugged in everything, everything fell into place pretty nicely because we don't have a normal force. We know that Fg is mg, mass times 9.8, so the mass of 10 times 9.8 gives us 98 newtons. And then the Fay we found earlier, which is right over here, 40 newtons. So then we know that if we combine these two, then it's Fn minus 138. You add 138 to both sides, and then your normal force comes out to 138 newtons. Now for our second formula, all of our forces in the x direction, we have our Fax that we found earlier right up here, minus force of kinetic friction. Kinetic friction is mu times normal force, as we stated earlier. The mu is 0.2, which was given in the original problem over here. And then we actually just found out our Fn right here, so that 138 was very useful. And then now we have everything we need except our acceleration. So if we just divide both sides by 10, then we end up with a final acceleration of 4.17 meters per second squared. All right, now we're completely done with this setup over here. Now let's go ahead and analyze the second one. So the second one, we basically have the same triangle. It's 30 degrees above the horizontal, but pulling upwards. So the main difference is going to be this. We have an Fax going this way and an Fay going that way. So really the only difference is the Fay. So if you take a look at this horizontal component, it's going to the right. This horizontal component is going to the right, but this vertical component is pushing downwards and shoving the mass more into the ground. And then this Fay is pulling up a little bit and releasing some of the force of the mass is applying to the ground. So we're going to basically set up the same exact formulas. It's going to be the sum of forces in the y direction is Fn minus Fg, but then this time a plus Fay, because this one's going upwards like our Fn. That still equals 0 because there's no movement or acceleration in the vertical direction. So our Fn is still unknown. Our Fg is still 98 newtons, mass times 9.8. And then this time we're going to add the 40 newtons as opposed to the first one where we subtracted it right over here. Okay, so that equals 0. So this time our Fn is going to drop quite a bit, and it's going to be 58 newtons. And as I said before, the Fay is helping the normal force support the mass so that the normal force doesn't have to work quite as hard pushing upwards perpendicular from the surface. Now let's go ahead and work out our second part. We have the Fax still driving the mass and the FFK still counteracting it. So this is still going to be 69.28 to 8 newtons, and then minus mu times our new normal force of 58. Okay, so obviously this one is 0.2 times 58 as opposed to 0.2 times 138. So there is much less friction. So that means that our mass should be accelerating much faster. So once you subtract these and divide it by 10, your acceleration comes out to 5.77 meters per second squared. Okay, so we found our final answer. The second one is the one that's accelerating more, which the reason being is right over here and right over here. Because of this upward Fay, it helps the normal force, and then the normal force doesn't have to work quite as hard to counteract this 98 newtons. So it shrinks the normal force, and the normal force shrinks the force of friction because the force between the mass and the surface of the ground isn't quite as much as when it was pushed downwards into the ground. So then that's why when you subtract this smaller value of friction, you have a greater net force. So when you divide by 10, you have this greater acceleration of 5.77 meters per second squared. So I hope that was helpful to you. Thank you for watching and listening.